Dear friends, already I have discussed related theory related to the design of the key. Now quickly I am interested to give solutions of one or two questions. So this one is the question number one. A solid machine shaft 50 mm in diameter transmit a torsional moment of 1200 Newton meter. A square key is used. One side is equal to 1 by 4th the shaft diameter and whose length is equal to 1.5 times the shaft diameters. Find the dimensions of key and check the key for its induced shearing and crushing stresses. Obtain the factor of safety of the key in the shear and crushing when yield stress in the shearing and crushing are 350 Newton per mm square and 425 Newton per mm square respectively. Given here shaft diameter D is equal to 50 mm. So width of the key already it is the D by 4, that is the 1 by 4th of the shaft diameter. So 12.5 mm. Length of the key is 1.5 times the shaft diameter. So it becomes 75 mm. As the key is a square one, hence W is equal to T, that is the 12.5 mm. Now force responsible for shearing stress or crushing for the key we can get from the torsional moment divided by radius, that is the diameter by 2. So it is the 48,000 Newton. Then shearing stress induced in the key from the formula already discussed and derived, that is the shearing stress 2mt divided by Tw into L. So it is the 51 Newton per mm square. Similarly, crushing stress it is derived in the theory, and crushing stress is 4mt by dlt. So it is 102 Newton per mm square. Factor of safety, that is the failure stress for the shear is 350 Newton per m square and induced stress is 51 Newton per mm square. So ratio is the 6.86. Similarly, factor of safety in the crushing 425 divided by 102, that is the 4.17. Second question. A medium steel shaft transmits a torsional moment of 1960 Newton meter. The diameter of shaft is 58 mm. Select the standard key from the table 12.1 and check it for the induced unit shearing and crushing stresses. Obtain the factor of safety of the key in the shear and crushing. Assume the material of the shaft and key to be the same. So the from the shaft here diameter of shaft is given 58 mm. So use the design data book and you can get the value of the dimension of the key, that is the for for shaft diameter 58 mm. For this one is the data book for the Bhandari, and for the 58 mm to 50 to 58 mm width of the shaft, that is the 16 mm, and height is the 10 mm, and height is the 10 mm, and length is varies from 45 mm to 180 mm. So here the width is the 16, height is the 10, and length varies from 45 to 180 mm as shown in the data book. But we know the formula for the length, that is 1.5 d. So approximately 1.5 into 58, it is the value is 90. So take the value 90 mm. So this is the key designations. Width is the 16, height 10, and length is 90 mm. Now the question become easy. and you can only substitute the values for the shearing stress 2mt divided by dwl. So this you can get the value, substitute all the data given in the problem. It is 47 newton per mm. Similarly, crushing stress, that is the use the formula, and you can get the 150 newton per mm square. So factor of safety in the shear, that is the failure stress in the shear divided by induced stress 7.45, and failure stress in the crushing 425 by 150, so 2.83. Now one more questions I am interested to discuss. This one is the 12.4 18.7 kilowatt 1400 revolutions per minute motor has a steel shaft. The extension of shaft is the 75 mm. Diameter of shaft is the 45 mm. The motor pull out the torsional moment is 3.4 times the average pull speed torsional moment of the motor, and the shock factor is 2.5. Assuming Fs induced shear stress 55 Newton per mm square, Fc 110 Newton per mm square. Find the size of the key. Check the shear strength of the key against the normal shear strength of the shaft. So here power, you know the formula of the power 2 pi n t divided by 60. Here mt is used in the space of the t, that is the torsional moment. So torsional moment is the 130 Newton per Newton meter, but it is given that the motor pull out torsional moment, that is the 3.4 times the average pull load. So it multiply the 3.4 into 130, it is the 442 Newton meter. Allowable shear stress, that is the yield stress divided by factor of safety. Factor of safety is given 2.4. That allowable shear stress, it is the Fs. Fs is the permissible, but shock factor is given. So you have to divide this allowable divided by shock factors. And this is the 23 Newton per mm square. Similarly, allowable crushing stress 110 divided by 2.4, so 46 Newton per mm square. Fc is equal to 2Fs. It is derived in the case of the for the square key, that is stress in the crushing is 2 times the stress in the shear. Now extension of shaft is 75 mm. Thus the length of key will be 75 mm. Length of key will be 75 mm. Now to find the depth of the key, use the relations already derived. Fs is equal to 2mt divided by dwl, is that is 23 is equal to, use substitute this value, so w is equal to 10.9 mm. The cross section of the key will be, it is a square key, so w is equal to t, so 10.9 into 10.9 mm. A strength of the shaft with the key wedge. How can find the strength of the shaft when key wedge is used, is equal to k multiplied by a strength of the shaft without key wedge. So k is factor, and a strength of the shaft from the torsional formula shear stress into pi by 16 dq. Here k is obtained by the HF More, and it is the formula 1 minus 0.2 w by d minus 1.1 t by 2 by d, so k becomes the 0.82. Now the shear strength of the key divided by the shear strength of the shaft. So use the formula shear stress of the key, that is the LWFS into d by 2. Shear stress of the shaft pi by 16 dq into Fs into k. so it is become, you can get the value 1.3. That is, the strength is 1.3 times stronger than the strength of the shaft. So this one is the some questions I have discussed. Or you can try the more questions from the books. If whatever you books you have, like the Bandari books, Kormi books, you can practice some questions from these books. Okay, now in the next video I will discuss the coupling along with the key. So I will discuss this chapter in the other videos. Thank you for your patience.